Okay, hi. So this is a special video I make just to clarify a few things that some student asked me regarding the nodes, spiral node, proper node, um, the what else we have saddle point, all those things. All right. So I will explain in this video. Um, all those things, right? So let's call this video, because this is under video number 14 if I'm not mistaken. Yeah, video 14. So let's call this video as a 14b. 14b. Try to make it a little bit bigger. No. Right. Okay. So remember that we are dealing with the nonlinear system of the form we have x dot equal to p xy equal to ax plus by plus epsilon 1 xy, and y dot is equal to qxy equal to cx plus dy plus epsilon 2 xy. And we have a certain condition, one of pq and the partial derivative are continuous in neighborhood of 0 0, and we also have ad minus bc is different than 0, and we have the third condition that limits. First condition is p q p prime q prime prime with respect to xy. So I might write like px py qx qy, all these are continuous in the neighborhood of 0 0, and we have a second condition is that ad minus bc is different than 0, and also we have third condition, the limit of epsilon ixy, the nonlinear parts, over r. This is 0 as r goes to 0. This is for I equal to 1 2, where r is the distance to the from any point xy to the 0 0, where r is a distance at square root x squared plus y squared. Now we say 0 0 is a simple critical point. Remember that 0 0 is simple critical point. Simple critical points means if the system, the given system, the nonlinear system that we have here, satisfy all these three conditions, and 0 0 is the critical point, so therefore we call 0 0 is simple critical points. Okay, now if we let the trajectory of let's say the trajectories of those nonlinear system, trajectory of nonlinear system, this one, we transform into a polar coordinates, in polar coordinate, that. So then our trajectories becomes like r equal to rt, w wt, or you want to call it omega, is still okay, where rt is positive, where x is rt cos wt, and y equal to rt sin wt. So we have a couple of definition, which need to satisfy in order 0 0 in order to the trajectories to be spiral point or knot point or proper knot. And apart from that, you need to understand that the stability of the system, what does stability means? If we have a neighborhood, I mean 0 0 is there, and we have delta neighborhood, we have epsilon neighborhood. So if the trajectory, if the trajectory is just goes beyond around that critical point, so but it's not going out of that epsilon neighborhood, so we call this as a stable. We call that as a stable. If it goes out of that, so if you have critical point here, we have delta neighborhood, we have epsilon neighborhood there. So this is delta neighborhood, this is epsilon neighborhood. Then if we have the trajectory of that, it means it goes out of epsilon neighborhood, so that's we call unstable. So this case we call it stable. This case we call it unstable. Okay, and if the trajectories as t goes to infinity approaches the critical point, so we have, this is the critical point, this is the epsilon delta neighborhood, we have epsilon neighborhood, this is delta neighborhood, epsilon neighborhood, and we have the trajectories look like that. So it goes toward the critical point. So in this case, we say the trajectory is asymptotically stable. Asymptotically stable. So we have three cases of stability. We have stable, unstable, or asymptotically stable. So all these cases, stable, unstable, and asymptotically stable, has been given in the previous videos, complete with the example. Now, regarding the what we call the form or the shape of the trajectories. So we have a couple of definitions that we need to know. The first definition, that if we assume some neighborhood u of the critical point, so if you have, this is the critical point u, the definition. If you have this critical point is here, and some neighborhood of those critical point that we call as u, where the critical point, this critical point is the critical point for the nonlinear system that we have up here, the critical point for that nonlinear system, then we have the condition that the trajectories defined, all the trajectories defined, you know what we mean by define, when t from t naught to infinity, or from minus infinity to t naught for all t naught, and also we have the limit of rt equal to 0 for for t goes to plus minus infinity. We have these two situation or condition for the trajectories of the for the system near the critical points. Okay, then we have we define, then we say a critical point, a spiral point, a spiral point, if the limit of magnitude of Wt t goes to plus minus infinity, this is 0 for all trajectories in u. For all trajectories in u. So that we call it a spiral point. So in this case, the spiral point look like that. Okay. Now, if the direction of those spiral goes toward the critical points, and if it goes to critical point, then we call it asymptotically stable. Yeah. If the direction away from the critical point, so we call the system unstable. It's a spiral point, but unstable. It's a spiral point with stable. So we have two things there. Spiral, either is stable or unstable, or asymptotically stable, depend on the direction of the trajectories. All those I have discussed in the previous videos. Okay. Oh, I'm missing. Just miss again that figure. Okay. So this, if the trajectories moving towards the critical point, so this we call it stable, and if goes if you approach the critical point 0, 0, then we call it asymptotically stable. So it goes away from the critical point, the direction away from the critical point, so we call that as a unstable. So for the spiral case, it's clear. So let's say we have the critical point here. Okay. Let's say, and this is the U neighborhood. Okay, and then we have the critical point. I mean the spiral point. Spiral point, we have that it goes out of U and getting bigger and bigger. So if it goes away from the critical point, the direction away from the critical point, so this is because spiral critical point unstable. Okay, and we say for the second case we have node, a node. If the limit of magnitude of Wt t goes to plus or minus infinity, give you some constant c, for all trajectories in u. So which means in this case, if we have, this is our critical points. So for the node we have, let's say this is our xy axis. Okay, so we have that and that and that and so on, and we have some more here. Let's say we have some more here. Oh, it passed through the critical point, so the direction is toward the critical point. So in this case we call it as a node. All right, again, if it approaches the critical point, then we say it's asymptotically stable. If the direction away from that, then we call it as a non-stable. Okay, in this case, W is the argument of our cos and sine in the polar coordinate system. This is our W. Okay, now we also have what we call proper node. Okay, a proper node. So what is a proper node? If the limit t plus minus to infinity Wt equal to c. So the difference between node and proper node, this is proper node and proper node, where for node we have absolute of Wt, whereas for node whereas for proper node we have without the absolute value. So W could be negative. W could be negative. So for the proper node, we have the trajectories in the form of a straight line. I think I given the example for this, why we have this kind of form, right? And if it points out toward the critical point, yeah, if the trajectory points toward the critical points, so we call it this as a stable proper knot. Yeah, stable proper knot. If it goes away from that, so this is unstable. Okay, and we also have improper knot. Yeah, we also have improper knot. Improper knot. If the trajectories look like the direction is mixed. Yeah, some goes inside like that, and some goes that. Yeah, the direction is toward the critical point, others away from the critical points. So in this case, we call it as a improper knot. Okay, then we have center and a saddle point. So what is the center and what is the saddle point? So we have a center, the critical point, 0, 0. Yeah, we call it center. Center. If in word I can say, if there exists a neighborhood of 0, 0 containing countably many closed trajectory, each containing 0, 0 and whose diameter tends to 0. What does it mean? So it means center, if you have the trajectory here, okay, we have or there exists a neighborhood of 0, 0. So we have many, yeah, countably many neighborhood of 0, 0. All this we call it neighborhood. Okay, that. And each of these neighborhood, let's say the innermost, the second, and the third, all of this, the critical point lies inside that. Okay, the critical point lies inside the trajectories, and the diameter, you can see the diameter from this is big and small and small and small and can get small and get small and get small. So the diameter goes to 0 or tend to 0. So in this, for the center, yeah, for the center knot like this, we only have one, which is the stable knot. We have stable knot regardless of the direction. So we have the stable knot. Why? Because if we consider that as a neighborhood of U, neighborhood of 0, 0, it's still in U. It not goes out from U for each of those trajectories. Okay, and we also have, that's for center, we also have what we call a saddle point. Yeah, so a saddle point, what is the saddle points? If we have two trajectories, so if you consider this, yeah, if you have two trajectories, approaching the critical point 0, 0 here, so one trajectories approach that, another one approach that, so two critical points approaching the two trajectories approaching the critical points, and others away from that. So others away from that. Okay, so if you plot others trajectory, it will look like, you know, along the y-axis, so we have that, and along the x-axis we have like this, and we have like this, that, and that, and that, and that, 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 and the direction along the y-axis toward the 0, but along the x-axis away from 0, goes to infinity. So same thing with this, same thing with that, and as well as this. So you look at the arrow, must be same direction, that. Okay, so this we call it as a saddle point. So for the case of saddle point, you can see the if we have the, let's say, U neighborhood here, so you can see there are many trajectories that goes away or outside of that neighborhood. Okay, outside of that neighborhood. So in this case we call it unstable. For the saddle point, if you have the trajectory is of the form of saddle point, then it is unstable. Our system is unstable. Okay, so that's the extra explanation that I can give, because I think in video 14 someone told me that in minutes at minute 16 or something, some part you cannot see. So I hope this one make things more clearer. Okay, so with that I stop here.